First, thank the organizers for giving me this opportunity to talk to you today. What I'm going to talk about is roughly based on my PhD and a little bit also on work ongoing with my former PhD advisor, who was Thierry Bodino. So my main field of specialty is hydrodynamic limits, who some of you may know that it's quite a technical subject, but I'm going to try to be as untechnical as possible tonight. But please, if I'm not making sense of, or if I'm not being clear, do not hesitate to ask a question. Also, since I'm going to be untechnical, I'm going to be not as precise as I should be from a mathematical standpoint, but I'll hope you'll bear with me and forgive this lack of precision. So my main focus for this short talk is going to be active matter. So here I gave some form of physical description of active matter. But in a more intuitive sense, maybe think about a large cluster of particles. And each of these particles is imbued with a velocity, with a direction for its motion. And each particle is able to change the direction of its motion according to some rule. Okay, so mainly this is very different, for example, than the influence of a field, of an energy field, because the field locally would affect all the particles in the same way. Okay, so for active matter, really the particles are independent and they're able to realign their motion alone. Somehow depending on the other particles neighboring them, but really individually. So why is active matter and active systems, why are they of interest? Is because they have quite a rich phenomenology. I'm just going to mention two phenomena that can occur with active matter. The first one is alignment phase transition. So this is a matter that has gathered a lot of interest in the recent decades, starting with a pioneering model by Vicek and his co-authors some 20 years ago. And Vicek and his co-authors discovered that actually for a system where particles tend to align their speed with their neighbors, you can have some emergence of a global order, which means that if the particles locally are going to align, you can have a global alignment which goes way beyond the real scale of local alignment. So you have propagation of order in some sense. And this was the start of a large study of these collective dynamics models. And actually, it appears that there is some universality here. So I wanted to mention it because it's really important from an active matter standpoint. This phenomenon is very important. The second phenomenon which I'm going to mention, which is going to be really my focus for this talk, is motility-induced phase separation. So the basic principle of motility-induced phase separation is quite simple. Imagine that you have a system of particles and that the particles slow down in the crowded areas. So when the density goes up, the velocity of the particle is going to go down. So this is quite a natural thing to expect. Imagine, for example, a flock of birds or a group of pedestrians. You're going to slow down in the crowded areas. And actually, for such a model, you can have emergence of motility-induced phase separation, which I will call MIPS later on. And the picture you see here is a representation of this phenomenon. So for passive matter, imagine a random walker in a nice environment. You would expect, in the pictures below, you would expect time to go from right to left. But actually, for this random walker, which will slow down when in the crowded areas, time goes from left to right, and you have a spontaneous apparition of this kind of dense cluster. So here the color represents the cluster, and of course the red cluster are very dense, and the blue and white cluster are not very dense. So this is really the coarsening effect I'm taking a look at. And actually these images are taken from an article by Cates and Tyre in 2012. Okay, so the first question I'm going to address here is, can we design a model, so a microscopic model, with purely microscopic interaction? So this is quite important, but I'm not sure I'm going to have time to address that, for which we can derive a hydrodynamic limit. So for those of you who are not familiar with the term, don't worry, I'm going to get back to that later on. But think about a large-scale limit for these models, and susceptible to exhibiting some MIPS-like behavior and maybe some alignment phase transition as well. But here, my focus really is going to be MIPS. Okay, so the first question is, can we derive the hydrodynamic limit for a model? And the second question, which is another thing altogether, is, are we able to mathematically prove this coarsening effect, this motility-induced phase separation for these models? Okay, so the first one, the answer is yes. The second one, the answer is maybe, but we're not there yet. Okay, so let me present to you a two-dimensional model, which is going to be our first try tonight. So you have two types of particles, so the green and purple particles, which I'm going to call plus and minus particles, which are moving on a grid. So this grid has a mesh size 1 over n, and with a side of n sides, so you have an n by n grid, a grid of n side by n side, sorry. And for each side in this grid, you're going to define a sigma x, which is going to be either -1, 0, or 1. So minus or plus 1 is going to represent the fact that the side of the grid is occupied by a purple or a green particle, and 0 is for an empty site. Okay, so this is the basic definition of a configuration for my model. Now, we want to start from some smooth initial condition. So we're going to consider two macroscopic profiles, rho 0 plus and rho 0 minus, which are two smooth functions in from 0, 1 squared to 0, 1. And we assume that the total density, so this is rho 0, which is the sum of these two profiles, is less than 1. And this is really going to represent the local initial density of particles in our microscopic model. And initially, we're going to start from local equilibrium, which is a nice thing to have, which means that, so if you take your grid, initially, each site is going to be filled up independently. And each site is going to be filled up according to the following rule. So the site X here is going to be filled with a particle plus, respectively, minus, with probability rho 0 plus, respectively, minus of X. And it's going to be left empty with the complementary probability. Okay, so we have our initial distribution, which fits some macroscopic smooth profile. We have defined the configuration. Now the question, of course, is what kind of dynamics are we going to define? So there are two main parts in the dynamics. The first one is the displacement of particles, and the second one is the realignment, because I mentioned that for active matter, we want the particles to be able to realign and change direction for their motion. There are two components for the motion of particles. The first component is a symmetric motion. So this displacement of particle is going to happen at rate n squared for each site. So each particle is going to jump at rate n squared to one of its neighbors. And if the neighboring site, is already occupied, we're going to cancel the jump. So this is called the exclusion rule. And it's really important for this model, but I'm going to get back to that later on. The second part of the displacement is a weakly asymmetric rate. So we want our particles to have some preferred speed, some preferred direction for their motion. So we're going to put a little bit of asymmetry in there. And this asymmetry is going to scale like lambda n, where lambda is a parameter and n is the size of the system. And the difference between the plus and minus particles is that the plus particles are only going to go to the right with this asymmetric rate, and the purple particles are only going to go to the left. Same thing, when a particle tries to jump on an occupied side, we cancel the jump. Okay, so here you have full exclusion, which means that any particle that tries to jump on an occupied site, the motion is going to get canceled. The second part is the realignment. So we want our particles to be able to change the direction of their motion. So an easy way to do that is through some Glauber, so some Ising-like rates. So here a particle is going to look at its neighbors, and it's going to try to mimic their behavior. So here, most of the neighbors of these particles are going to the left. So this particle is going to try and do the same. Okay, and we're going to tune that part with some parameter beta, which for those of you who are familiar with the Ising model is the inverse temperature for this part of the dynamics. But actually, we have I chose these rates here, but we have a broad margin of rates that would be acceptable for these dynamics because it's not accelerated in n. Okay, so this really occurs, this type of updates occurs really not very frequently. Okay, so is the model clear so far? Okay, so now I'm coming to my main topic, which is the hydrodynamic limit for this model. So the broad question behind the hydrodynamic limit is what can we do, what can we say about the macroscopic profile? So in order to keep track of really all the importance quantities for our model, let us define the eta x, which is going to be the absolute value of sigma x. So eta x is only equal to 0 if the site is empty, and is equal to 1 if the site is occupied. So eta x, in some sense, is going to represent the total particle density regardless of their type. And now we want to make sense of the limit, so rho and m. So rho is going to be the density, and m is going to be called the magnetization, which is the local strength of the asymmetry, the local flux of particles who want to go to the right with respect to the particles who want to go to the left. So we want to make sense of this limit of the expectation of eta x of t. So of course, there's a scam here. There's a scam because eta x and rho and m are not really going to live on the same space. Here, eta x and sigma x live on the grid. Whereas we want our functions rho and m to live in the continuous domain. So here you have a scaling limit, which I'm going to need to make sense of. And actually, a nice way to do that is through a weak formulation of the macroscopic evolution. So we're going to consider a nice smooth function h. And we're going to try to prove that for any such function h, for any smooth function, the average over the grid of h over x eta x of t is going to converge to the continuous integral of h of x with respect to this measure, this density rho of tx. And yeah.
X over n on the left? Or?
No, because it's x is...
Okay, so my mesh is of size 1 over n. So the grid is naturally embedded in 0, 1 square. This is a little trick to simplify notations. Okay, so the question is, can we prove that we have such convergence? Can we prove that these two profiles, rho and m, exist? And the more interesting question, of course, is what can we say about the evolution in space and time of m and rho? So the answer is the following result. Assume that initially your total density is less than 1 everywhere. Then the macroscopic profiles rho and m are solution in a weak sense. So this is a very unprecise formulation, but bear with me, of this reaction diffusion coupled system of differential equations. So here you see that the evolution of the total density has some Laplacian. So this is due to the symmetric evolution. And some gradient of m1 minus rho, which is a drift term, which comes from the fact that the plus and minus particles are going to have a drift in different directions. Okay, so for example, if m is equal to 0, there are as many plus particles as there are minus particles locally. So there is no drift. The problem is that the evolution of the magnetization is much nastier. It's much nastier because the ds of rho is called the self-diffusion coefficient, and it's not an explicitly known function. This is known through a variational formula, and this is known through a variational formula as well. So we have some estimates, but this part is nasty because this coefficient can go to 0, and when you lack diffusion, you have some problems for your system. Okay, so actually this system is not very satisfying because of these reasons. For example, we cannot prove, or we didn't succeed in proving some uniqueness for the weak solution of this system. So this is really painful, and this is why I can't have a better formulation than in a weak sense. Okay, so one part of the problems come from the exclusion rule, which makes the model non-gradient, and also which makes that the model has a very slow mixing. So example, if you start from a configuration which looks like that, you would like your system to be able to move to something which resembles more this picture here, which resembles more closely to a product measure. But actually, because of the exclusion rule, the only way to go from here to here is through the realignment dynamics, and this one is very, very slow. And you want this to happen almost instantaneously. Okay, so the diffusion coefficients are not known, and uniqueness is hard to obtain because of the degenerate coefficients, or because of the asymmetry, and because of the fact that we have a cross-diffusive system. So one possible solution, I told you that most of our problems come from the exclusion rule for the symmetric part of the dynamics. So one possible solution is to relax a little bit this part of the dynamics. So now I'm going to consider a 1D model to make notation simpler. And this time, for the symmetric evolution, we're going to allow two neighboring particles to swap. Okay, so actually this seems like a small change, but this changes quite a lot the proof. We keep the exclusion rule on the asymmetric part because we want to be able to maybe recover some mixed-like behavior. And now the hydrodynamic limit can be proved much, much easier. And actually, the system is much nicer. Here, you have fully explicit equation. This part is linear. This part is linear. These parts are quite nice. And now you have a couple of equations that you can work with. OK, so now we want to recover, or try to recover, some MIPS-like behavior by letting the asymmetry go to infinity, so by letting our particles have a more and more important drive in a specific direction. And to do so, we're going to have to scale also the realignment part. So here, I put a factor gamma here, which is a little bit a cheat. But it's sufficient to accelerate by gamma the corresponding part of the dynamics. And I'm going to assume that gamma scales like lambda square over 2c, where c is some positive constant, and lambda was the strength of the asymmetry. Now, I can rewrite the previous system, the previous two equations. And now I make this replacement. So gamma is lambda square over 2c. So now you recover some terms of lambda. And in the second line here, so what I'm going to describe now is very formal. It's not supposed to be rigorous. It's just for you to see where I'm going with this. So now we can divide everything by lambda. And formally, we can obtain that this term is going to go to 0 because we divided it by lambda, this term as well. And we're left with 1 minus 2 rho dx of rho, which is equal to lambda n divided by c, plus some correction. So this means that lambda m is a function of rho, and we can re-inject it formally in the first line, and we obtain a diffusion equation. And this diffusion equation is nice because, first, it's autonomous in the density. So now we have completely thrown out of the picture the magnetization. And also, this part can be negative for some large densities. And why is this nice? Because this is essentially the point of motility-induced phase separation of the coarsening that I was mentioning at the start of the talk. OK, so for rho superior to some critical value, we can have a negative diffusion coefficient. So a positive diffusion coefficient is going to smooth out your density. A negative diffusion coefficient is going to pack your particles back together. So this is really what we can expect. Of course, there is a lot of scams here. There is much non-rigorous stuff. So the question is, can we recover this limit rigorously? And answer yes to my second question of earlier. And one possibility, which is the subject of my ongoing work with Thierry, is to actually let lambda go to infinity, but on a microscopic level, so with n, and try to recover a hydrodynamic limit from the microscopic model, and try to derive rigorously this hydrodynamic limit. Okay, but we're trying to use a method that's called the relative entropy method, and there are a lot of hurdles here, because once again, because of the exclusion rule, even only on the asymmetric part. Okay, so I think I'm going to stop here. Thank you for your attention.
Questions? Okay, so I have a question. If you allow birth and death of particles,
yeah,
would it change? I mean, would it make your dynamic mix much faster and obtain something different, or? Okay,
so actually, allowing death of particles would maybe allow to relax a little bit faster, even in the first model. It depends on what scale you do it. If you scale it like the Glauber dynamics, which is the realignment dynamics, then you're probably fine. Because anyway, the local equilibrium is going to be prescribed by your diffusion part. So this is going to be essentially a product measure. So if you allow burst and death of particles, it's going to only help to create some holes. So I guess it should be fine. And it should be fine, and maybe it should help, but the problem is that since the Glauber part is very slow, you need some instant mixing. So I'm not sure that it would help to mix instantly.
Do you have any kind of phase transition?
OK, so this is the end goal, and especially for the alignment part of the dynamics, which I didn't really address here. So the initial goal for my PhD was to try to get some sense that we had a phase transition if you had some alignment mechanism like in a V-check model. But for this kind of model, we're really, really far from this goal, especially because we don't know how the first system of equations behave. We have not really any idea, even if some basic question like uniqueness have no answer so far. So much harder question like phase transition for this type of equation are way out of our scope for now.
I think we can thank Clément again.
Oh, sorry.
Posso fazer assim?
So next speaker is also a local, Roberto Imbuzer Oliveira, and he's going to tell us about local minima of the SK model.
Well, thank you all for being here so late. I'm not that local, I'm from 2 floors above, you know. So, but this talks about the SK model, but not necessarily about the things that you heard about this morning that might have heard about from the works of Talagrand and Panchenko, so bear with me for a little bit. So the SK model is just this very simple looking thing here. We have a state of spins, so we have n particles, say they have a state that's either +1 or -1, so that's like a discrete hypercube. We have these random variables which are ID standard Gaussian, and we consider this Hamiltonian. We can just say a function defined over this space, which is, well, the sum of sigma I, sigma j multiplied by these weights, which are Gaussian and random, right? So, okay, it's a random Hamiltonian, but maybe for today's talk, the way we're going to think about this is as just a very simple example of a random function. And we want to understand properties of this random function, right? So the physics part of the SK model is not going to play a role here. Right, so as I said, right, we want to understand this function. And there's a very celebrated result by Talagrand confirming a formula that was put forward in the physics literature by Giorgio Parisi, which says the following. So if you compute the minimum of this function on the hypercube of size n, right, the minimum over sigma, and you divide that by n to the 3/2, and you put a minus because you want to have a positive number. When n goes to infinity, so the more and more spins you have, you're going to get this closer and closer to a constant. Well, this converges actually, I mean, the sense of expectations, but also more surely. And this constant is positive, and it's given by a very complicated formula called the Parisi formula. That was the main result by Talagrand. Well, since that paper, which is maybe from 10 or 12 years ago, there have been a lot of progress in properties of the Gibbs measure given by this Hamiltonian, but as I said, we're not going to be talking too much about this. There's a very nice book by Panchenko about this sort of problem. There have been many, many more developed since this book's been written, which wasn't so long ago. But anyway, so our problem today is to understand local minima of this random function. What's the local minimum? So we're just going to stick with the simplest possible definition. So sigma, maybe I should just write it as here. Sigma, as I said, is just a configuration, right? So it's just a vector of plus and minus ones. And we say that this sigma I here is what you would obtain if we take sigma and we keep all coordinates except that we flip the ith coordinate, right? So if the ith coordinate of 1, we flip it to -1 and vice versa. And the local minimum, by definition, is a configuration of spins whose neighbors, right, so such that any other configuration that you can obtain by flipping one single site has larger energy than sigma itself. And, okay, this is the function again. And our questions are, the questions we're going to answer are very simple. We're just going to understand how many local minima there are and what's the typical energy of a local minimum. Right? So, okay, why would you want to answer this question? I mean, this is not necessarily the first question that comes to people's minds. I mean, it's apparently one of the last since people have been working on this for a while now. And, well, so the way we think about it is that we want to gain some insight on this random function, right? So it's, we want to understand what this, well, we could call it an energy landscape, I guess, looks like, right? And this seems like an obvious enough question that hadn't been explored. It will turn out to be the case that most local minima have similar depth in the sense that there's a constant, a fixed constant, such that essentially all local minima lie within a very small band of this value. Right? And the other reason why you might want to be interested in local minima is that It turns out that by a recent paper by Omer Angel, Seb Bubek, Yuval Perez, and Yufei Wei, you can find these local minimum in polynomial time, but just by a greedy algorithm, right? Whereby, well, you take your current configuration, you look into whether there's a coordinate that's going to decrease your energy value. If there is such a coordinate, you just flip it, and you keep doing that. What they proved is that in polynomial time, maybe n raised to the 11th or something like that, this process would stop with the local minimum. And it's an interesting question to understand how such local minimum compare to the global minimum given by the Parisi formula. Well, there's a caveat here which you can't really address at the point, which is that these local minima are not necessarily the ones that our local minima are not necessarily the ones that the algorithm finds, right? So the local minima that the algorithm finds are not necessarily uniform of all local minima or anything like that. But in any case, I mean, it seems interesting to understand local minima, right? Okay, so what are the results? First result is that we can compute the expected number of local minima up to exponential order in this sense, right? So the expected number is 2 to some constant alpha times n plus smaller order terms in the exponent. And this alpha is given by some simple variational principle coming from some large deviations function that I'm going to describe towards the end of the talk. Second is, okay, this is a bit harder to read, but it's saying this. So take any configuration spins and condition on it being a local minimum, right? What's the conditional distribution of this energy here? And here I'm normalizing by n to the minus 3/2, so, which is the same order of magnitude of the Parisi minimum, right? And it turns out that this quantity here behaves in a very non-random manner in the sense that it's very concentrated around a value here, nu star, minus nu star, right? Up to lower order terms. Well, in this precise sense here, if you condition on having a local minimum, and you look at this energy, and you look at the difference between that and minus nu star, the probability that this is large is exponentially small. Okay. This also comes from a variational formula. We're going to see the formula at the end if you're curious. I mean, but maybe the most interesting thing is just to see where this comes from because it's very simple and very, well, once you decide what to do, right? When you choose this problem to solve. Okay, so what's the proof like, right? So clearly we have to worry about these quantities here, which is how much the Hamiltonian increases when you flip I, right? Or it could decrease as well. But of course, since we're worried about local minimum, we want this to be larger than 0. And in fact, if you look at these random variables, I mean, each one of them individually, I'm dividing by half just for convenience. Each one of them individually, okay, this is sort of unfortunate because I have n and n here. Each one of them is a normal random variable with mean 0 and variance n minus 1. And well, the property that sigma is a local minimum is precisely the property that all these variables are positive. And okay, and this is a random vector, right? x1 up to xn. What's the distribution of this random vector? Well, it's Gaussian, so we just need to compute the covariance matrix. And this is what it looks like. It has n minus 1 on the diagonal, which comes from this. It has this 1 terms off the diagonal, which just means that if I look at xi, x sub I, and x sub k, there's 1 term in which they overlap, and all the other terms are independent. Okay, so it's very simple. And since it's very simple, you can try your hand at computing this probability that sigma is a local minimum explicitly, right? The event is here, and you just want to compute the probability of this event under some high-dimensional Gaussian measure. The covariance matrix is simple. It's a rank 1 perturbation of a multiple of the identity. So, well, the formula would be this, right, if sigma n is the covariance matrix. And it turns out by doing lots of changes of variables, you get an explicit formula in terms of a standard normal random vector in n dimensions. So this guy here is a random vector with IID standard normal coordinates in Rn. And the probability of the event that we're looking at is just this number here, right? So basically, we have to evaluate this expectation in order to compute the expected number of local minimum, right? Because this is the probability that individual configuration is a local minimum. Just take 2 times n, 2 to the n times this, and that's the expected number. Right, so, okay, this is just saying, okay, the asymptotics of the log of the expectation are just the asymptotics of the log of this expectation over here. Well, we know how to compute this expectation. Basically, we can write it explicitly. We get something like this. We get this this is the, look, this is the, yeah, I'm not sure if I emphasize this. This is the L1 norm of a vector, right? So it's not the Euclidean norm, which is easier to understand. It's the L1 norm. And this L1 norm, well, you can compute its expectation, you can compute its variance. And it turns out to have fluctuations of an order that requires that you analyze this integral here using large deviation techniques. Okay? It could be that somehow the fluctuations of this quantity here, the exponent, were negligible and we could just replace what's inside by an expectation. That's not the case, so we get something that you can address using, say, some version of Verdon's lemma in the large deviation theory to get the sharp constant. But it's also not hard to use the log sub 11 equality to analyze this and get, for instance, that this expectation, well, the log of it divided by n is between these two constants, right? The actual value comes from a formula that I'm going to show in the end. Right, so, okay, so this is question number 1, right? It's about the expected number of local minima. What about this energy distribution when you condition a configuration of being a local minimum? So, okay, so we had these variables x sub I. And I mean, the event of a sigma being a local minimum, as I said before, is just the event that they're all positive. But it turns out that we can also write the Hamiltonian in terms of these guys. Because you see, here I just have sigma I, sigma j, wij for a fixed I, right? So if I sum these guys, we'll normalize properly to get the same normalization I had before. I have this sum. And yeah, and then you can write, okay, the event that the energy of the Hamiltonian minus it divided by the answer to 3/2 is larger than delta is just this other event here. So again, it's an event involving these same random variables that I had before, right? So these are Gaussians with a specific covariance structure. Okay, so what comes out of this? Well, what comes out is that you can write down this conditional probability as another kind of integral where somehow large deviations are going to play a role, right? So I have here the expectation that I had before. This is just a probability that sigma is a local minimum. And on the numerator, I have this exponential integral multiplied by an indicator here that concerns the L1 norm of this Gaussian random vector. Right now, it's a standard Gaussian, as I told you before. So it's, well, again, once you set your mind on this, it's not that difficult to work it out. If you know the tools to use, like things like Verdon's lemma, we can write down the Laplace transform with this guy explicitly, well, more or less explicitly, so it's all good. Right, so, okay, I've been telling you about these formulas, and I haven't really said what they are, right? So what are these formulas like? Well, I said they are variational formulas because they come from large deviation kinds of things. But here is sort of it turns out that all of them are kind of, I wouldn't say they're quite explicit, but we can write it down in a form that doesn't involve variational formula. There's just some equations for them, right? So, okay, this is just a cumulative distribution function of the normal random variable. This is the log of twice this thing. Now, for each x, I can compute this value lambda star of x, the unique lambda for which that solves this equation. We have to prove that it exists, but it's not hard. And now you have this nu star, which is the unique nu for which nu equals twice lambda star of the same nu. So it's a kind of fixed point equation for nu. Once you get this guy, and this is going to be exactly the energy of a local minimum, right, up to normalization assigned. And once you have this guy, you can compute the alpha. And alpha, remember, it's just the exponent in the formula for the expected number of local minima. And I mean, I'm showing these formulas just because I guess I have to. But the important thing is that essentially all come from the large deviations principle for the L1 norm of a standard Gaussian random vector in high dimensions. Right? So you have to work with it a little bit. I mean, and the nice thing is that these are all one-dimensional problems, so we can do numerics with these things. Okay, what kind of numerical question would you want to answer with this? Well, okay, here's one natural question. We have this local minimum value, right? So if you have a local minimum, its energy divided by n to the 3/2 should be close to minus this. And of course, we have the global minimum, which is given by the Parisi formula. Right? So you can ask, as I asked before, right? So how close are local minima to global minima? And well, I wrote these numbers down, and maybe I shouldn't have, because we're a bit, we still aren't quite sure about the numerics here. So there are things we need to check. But it looks like from our preliminary studies that actually the value is surprisingly close to Parisian, right? So okay, it's good up to 1 decimal digit, if you want to put it that way. Right. So it seems interesting that somehow requiring something much weaker than having a global minimum still gives you a similar energy value. Right? But perhaps more interesting is asking questions that are related to this and take you towards the full Parisian solution. And okay, so these are the open problems, and I guess it's going to be quite quick. Right, so the first open problem is that we only have bounds for the expected number of local minima. We have no idea what those values are typical, or somehow, it's only an expectation. What can we say about the actual value? In principle, it's just a second moment calculation, but if you look at it, you're going to be as scared as we were. Or maybe not, and then you can solve the problem. Right, so another question that I think is very interesting is we want to relate these local minima that we find, right? Just, we condition a configuration being a local minimum. What about these local minima that this greedy algorithm finds? What can we say about them? Are they the same somehow? Are they different? At this point, we don't really know much. But this is like the problem that I like the most here. And we looked at a very simple definition of what a local minimum is, right? So it's just saying, well, a configuration is a local minimum if by flipping any single spin, I don't decrease its energy. So what about if you allow for flipping k spins? That would be a k local minimum, by definition. And the question is it true? Okay, this is a kind of very bold conjecture that's implicit here. It's saying, okay, if you take k large enough, this should get closer and closer to the Parisi solution, right? Okay, so the bold conjecture, I guess, is saying that k is a constant. Of course, finding the right k for which this thing goes to 0 would be a very interesting challenge. To see how large k needs to be in order to approach the true global minimum. Sorry. And of course, there's a minus sign missing here, I guess. But, and well, that's it. Thank you very much.
Questions?